Hey guys, welcome to the next unit. We are starting Chapter 10 and Chapter 11. We will be focusing on a big mix of different topics in here, but again, kind of similar to what we did with gas laws, where it's stuff you've seen before. It's not meant to be overly challenging. I purposely put these two chapters when I knew I was going to be gone from maternity leave because it's stuff I know you guys can handle. Hopefully Chapter 5, gases, went halfway decently for you. That chapter is challenging in its own right. It's not meant to be an easy chapter. Nothing in AP Chemistry is particularly easy, per se. But hopefully because you've seen gas laws, it was a little bit less challenging. The hard part of that chapter is really the problem-solving aspects of it. And we'll continue working on the problem-solving aspects as we move through the rest of this unit, or the rest of the semester, I should say, and start reviewing for the AP exam. But hopefully we feel halfway comfortable, and hopefully these videos are actually helping you. So let's kind of break down this chapter. This chapter we are delving into states and matter. So we just talked about gases. Now we're going to talk about liquids and solids. We'll be talking about phase changes and a little bit about colligative properties. So again, things that we're fairly comfortable with. We'll start out looking at solids, and we're going to talk about 4 different types of solids, which are ionic solids, molecular solids, metals, and network solids. And the big difference between those is going to be the intermolecular forces. As we're going through these solids and you start thinking, oh, I kind of like this, I would highly suggest you look into material science, because this is kind of the intro into material science. Obviously, we're not going into a lot of it, or even very in-depth. We're just kind of skimming the surface of it. But if it's something you like, check that out and see if you want to delve into that even further. We'll talk a little bit about liquids, specifically just really vapor pressure. We're not going to focus a lot on liquids. And you did intro a little bit into vapor pressure in the last chapter with the lab. From there, we will talk about phase changes. Specifically with phase changes, we're not talking about melting, boiling, freezing, that type of stuff. What we're actually going to be looking at is the thermodynamics of phase changes and heating curve calculations. And that will make more sense as we get to it. The reason we throw that into this chapter is because the next unit is actually thermodynamics in itself. So AP Bioworks, if you remember your delta G, delta H, and delta S, Gibbs free energy, enthalpy, and entropy, that's what we're actually going into. And some of you probably just had a little mini heart attack because you remember that being really crazy difficult in AP Bio. Keep in mind that in chemistry, even though thermodynamics is still a challenge, it is a little bit easier than when you see it in AP Bio, because you have the chemistry background to kind of give you some guidance on it. In AP Bio, when you don't have the chemistry, it can be very, very abstract and very challenging. It shouldn't be as bad, and hopefully I will be back by the start of that chapter, so that should help a little bit too. From there, once we go through phase changes and the thermodynamics of phase change, we will briefly talk about colligative properties. We will not be doing any of the math involved with colligative properties. You guys did that last year, and College Board does not recognize, well, not that it doesn't recognize, it doesn't have molality on the test in any way, shape, or form, so therefore the calculations of colligative properties is kind of a mute point. There's no point in it. Also keep in mind, as I'm making these videos, I do have Riley at this point in time, and she is next to me, so she does make some noises. So if you hear anything in the background, I apologize. It's probably just her. So let's go ahead and dive in and see where we are. Okay, so when we're talking about solids, there's 2 basic categories of solids. You have a crystalline solid and an amorphous solid, and they're exactly what they sound like. A crystalline solid is something that has a regular or predictable or consistent arrangement of their components. And we'll talk about what components means in just a minute. But what that basically means, it's this picture right down here. If you look at it, notice all of these, this is a zoomed in picture of sodium chloride. All of these crystals are very square or rectangular. The reason being is because the arrangement of the ions in the sodium chloride is very consistent. It's called a lattice structure. Okay, versus an amorphous solid is kind of this picture right here. Its components are more disordered or not consistent. Keep in mind, let's go back and talk a little bit about solids. Remember, what makes a solid versus what makes a liquid versus a gas is the intermolecular forces. And a solid has a lot of intermolecular forces compared to the other 2 states of matter. And also keep in mind, those intermolecular forces, because there are so many of them, are holding those components in a very strict or permanent position. So the only thing those components are able to do is just vibrate back and forth. They're not actually moving. Remember, solids have consistent shape as well as volume because of this as well. So in a crystalline solid, those specific positions that they're being held in due to their intermolecular forces are very regular or arranged. Literally, if we could zoom in on a molecular level, kind of like if we could see this picture for the sodium chloride, you would see a pattern of sodium, chlorine, etc. And there are different patterns. Again, we'll look at that in just a moment. Versus an amorphous solid, when you zoom in here, notice that, again, these are being held consistent. This kind of looks a little bit like what you might see in a solution. So you might be thinking, okay, these guys are moving around. They're not. They're being held in their position. But notice the position that they're being held in is very inconsistent, or very almost chaotic, if you will, or disordered. So that's kind of the big difference between these. Now, we will only really be focusing on crystalline solids in this particular chapter. We won't be dealing a lot with amorphous solids. Your book does talk a little bit about amorphous solids, so you're welcome to dive into that. But in terms of College Board, we really only care about the crystalline solid. The reason we focus on crystalline solids is because they're straightforward. Because their arrangements are consistent and their intermolecular forces are consistent, they have consistent properties that are predictable and easy to use to determine what the substance is. Again, those substances we'll be looking at is ionic, molecular, network, and metal solids. So let's talk a little bit about that lattice structure. Again, we're focusing on just the consistent structure here, not the amorphous ones. So with a lattice structure, what that basically is, scroll down here and you can kind of see it. This is a lattice structure, and there are multiple different types of lattice structures. These are just a few. And as you delve into chemistry, if you go in as a chemistry major, you will take a class called Inorganic Chemistry, not organic, inorganic. And it focuses a lot on these different types of structures because that affects the properties. Not only does the type of intermolecular forces affect the properties, but the actual lattice structure will affect the properties as well. So this is what we're referring to as a lattice structure. So again, consistent pattern. The components that I'm referring to are these little black dots on the vertexes. And those components will either be atoms, so it would be an atom for a network solid, so such as diamond is what we consider a network solid, so the only thing that makes a diamond is carbon. So each one of these dots would be a carbon atom, okay? It would be an ion if it is a ionic compound, so like sodium and then chlorine ions would make up these vertexes. And then you also have molecules, so water, for example, H2O would be these guys as well. So don't look at these black dots and think it's an individual atom. It can be multiple different things depending on the type of solid we are referring to. And then, of course, these black lines are our forces that are holding them together, whether inter or intramolecular forces. And again, we'll talk about that in just a moment. Okay, so that's a lattice structure. A unit cell, if you guys remember back to last year when we did stoichiometry, the good old days of having easy stuff to work through, huh? When we were dealing with ionic compounds, we called them formula units, if you remember. So we had atoms were individual atoms, of course, and molecules were our covalent compounds. But when we did ionic compounds, we called them formula units. Well, where did that name come from? It came from what's called a unit cell. So when we're dealing with ionic compound, this is a unit cell. It's also a lattice structure for anything, but that's what we're referring to as a unit cell. So it is basically it's taking the pattern and picking the smallest non-repeating of it. So it's basically like if you were to zoom in on a pattern, like say it's like a triangle, circle, back and forth. The triangle circle would be the smallest piece, and then that piece is repeating in itself, but within that piece there's no repetition. And then from there, when we get into inorganic chemistry, as you get into inorganic chemistry, you'll learn something called X-ray crystallography. Basically, that is shooting X-rays through these lattice structures and following the diffraction pattern, which of course is measured by the instrument. And then you're able to determine the structure of the solid that you're looking at. That's not anything we're going to get into, but just something so you can kind of see that it exists. It's pretty neat and pretty cool to look at. Okay, so let's keep going. All right, so again, solids or specifically the crystalline solids that we're looking at, are mainly different due to the forces that are holding those vertexes, or again, if we go back here, these little dots, holding those together. So these black lines are forces, whether inter or intramolecular forces. Depending on the strength of these inter or intramolecular forces, these vertexes will be held either very, very tightly or very loosely. So it all kind of depends. So let's kind of go back and rewind, talk about our intermolecular forces. Inter and intra again. intermolecular forces, we have our LDFs, our London dispersion forces. Remember, these are our weakest ones. Okay, these are going to be found in our nonpolar, if we remember those. So this would be something like our diatomics, for example. So like bromine, Br2. Remember, when we have our Lewis dot structure between two bromine atoms, the electronegativity is equal between them, so therefore nonpolar. So therefore the electrons may become unevenly distributed, which will cause a London dispersion force, or that very weak attraction. Our dipole-dipole is with our general polar molecules. So this would be something like, let's say, that's going to result in that. So let's say NBr3, which is our trigonal pyramidal. Our electronegativity will not cancel out due to this lone pair not pulling or pushing. So the bromines will be pulling against the nitrogen, which will result in a dipole, polar and, or a positive and negative dipole due to the electron uneven distribution, which will result in a polar molecule that will be attracted. The two positives, or the positive of one molecule attracted to the negative of another molecule. You also then have your hydrogen bonds, which again are your polar, but these specifically are nitrogen, fluorine, and oxygen, so like our H2O, for example. Okay. Now, from there, let's talk about the rest of them that we have to consider here. Electrostatic attraction, I believe we have talked about this before. This is between two ions, so this is actually what forms an ionic bond in all technicality. So kind of weird to think about the fact that an ionic bond is really a type of intermolecular force, not an intramolecular force. So we try to make the distinction very different, that inter is different than intra, but really the difference is the space between them. So think back to our Coulomb's law, Q1, Q2 over R squared. The only real difference between an inter and an intramolecular force is the space between them, so your radius. And that's what makes your intra stronger, because the radius is smaller versus your inter is more spaced out, therefore your radius is larger, weaker force of attraction. But an electrostatic attraction is just a type of ionic bond. So that would be our sodium ion being attracted to our chlorine ion due to the positive and negative. Okay? And electrostatic attractions are the strongest of these types of intermolecular forces. From there, we go into our... Again, sorry, Riley's making noise in her sleep. We go into our intramolecular forces, if you will, which is our covalent bonds, which is our sharing of electrons, okay, versus the transfer of electron and then the attraction of that transfer, of the electron transfer due to the positive and negatives. Now, in terms of covalent bonds, there's actually two types of covalence bonds. One's called a non-directional, and one's called a directional. And what that basically means, non-directional is where the sharing of electrons is not necessarily between two specific atoms. It's almost like the whole solid is sharing the electrons. So kind of think about it as like, hey, you bring a bag of candy to the classroom and everybody gets a piece. That's kind of your non-directional. Versus a directional covalent bond is if you bring a bag of candy, just you and your friend are sharing the candy. Okay, so these are very specific between two atoms or two species versus a bunch of things that are sharing them in the non-directional, and that does cause a difference in strength. So the non-directional are a weaker covalent bond than the directional. So this is very important to kind of keep in mind the strength here. London dispersion being our weakest, dipole-dipole, then hydrogen bonds, of course, and these are our very stereotypical intermolecular forces in terms of strength. Electrostatic being much stronger than these three, but still an intermolecular force, then non-directional covalent, and then directional covalent. Okay, so that's all the time I have for this video right now. What we're going to do is we're going to stop for just a minute and start the next video, and we'll talk about the types of solids and work through some of those. Thanks, guys.